Welcome. Today we're going to explore a fascinating application of Bayes' theorem that appears in active inference and probabilistic reasoning with generative models. The original problem asks us to understand how the equation P of S given O and M equals P of O given S and M times P of S given M, all divided by P of O given M, is derived from the standard form of Bayes' theorem. Let me start by reminding you of the fundamental form of Bayes' theorem that you're already familiar with. Bayes' theorem states that the probability of A given B equals the probability of A and B together divided by the probability of B. This can also be written as the probability of B given A times the probability of A, all divided by the probability of B. Now let's look at what we're dealing with in this active inference paper. We have three key quantities: O, which represents observations that we can measure or see; S, which represents hidden states that we cannot directly observe; and M, which represents the generative model, essentially our assumptions about how the world works. What we're trying to find is P of S given O and M. In other words, given that we've made certain observations O and we're working under a particular generative model M, what can we infer about the hidden states S? This is called the posterior distribution over hidden states. Now here's the key insight. Let me show you visually what's happening in this system. We have a Bayesian network, which is a graphical way to represent probabilistic relationships. At the top, we have M, the generative model, which acts as our framework or context. Think of M as the lens through which we interpret everything else. From M, we have an arrow pointing to S, the hidden states. This arrow represents P of S given M, which tells us, given our model M, what is the probability distribution over possible hidden states. This is sometimes called the prior over states within the context of model M. Next, we have arrows from both M and S pointing to O, the observations. The critical arrow here is from S to O, labeled P of O given S and M. This is the likelihood function. It tells us, if the hidden state were S and we're working under model M, how likely would we be to observe O? There's also a direct connection from M to O, which emphasizes that our model M influences how we interpret observations. All of this takes place within the context of M, which I've indicated with a box around it. Now let's derive the equation step by step, starting from basic Bayes' theorem. We want to find P of S given O and M. Let's think of this as a conditional probability problem where we're conditioning on both O and M together. Using the fundamental definition of conditional probability, P of S given O and M equals P of S and O and M all together divided by P of O and M together. Now here's a crucial step. We can rewrite the numerator, P of S and O and M, by recognizing that the joint probability of three events can be factored. Specifically, P of S and O and M equals P of O given S and M times P of S and M. Why is this true? Because the probability of all three things happening together equals the probability of O happening given that both S and M are true, multiplied by the probability of both S and M being true together. This is just the chain rule of probability applied to three events. So now our expression becomes P of S given O and M equals P of O given S and M times P of S and M, all divided by P of O and M. We're making progress, but this doesn't quite look like our target equation yet. Let's continue. Notice that P of S and M in the numerator can itself be written using conditional probability. P of S and M equals P of S given M times P of M. This is again the chain rule. The probability of both S and M equals the probability of S given M times the probability of M. Substituting this back in, we get P of S given O and M equals P of O given S and M times P of S given M times P of M, all divided by P of O and M. Now let's look at the denominator. P of O and M can similarly be factored as P of O given M times P of M. The probability of both O and M equals the probability of O given M times the probability of M. Substituting this into our denominator, we have P of S given O and M equals P of O given S and M times P of S given M times P of M divided by P of O given M times P of M. Here comes the beautiful simplification. Notice that P of M appears in both the numerator and denominator. These cancel out perfectly. After cancellation, we're left with P of S given O and M equals P of O given S and M times P of S given M, all divided by P of O given M. And there we have it. This is exactly the equation from the active inference paper. Let me now explain what each term means in this context, and why this formulation is so powerful. P of S given O and M is the posterior. This is what we want to compute. Given the observations we've made and our generative model, what should we believe about the hidden states? P of O given S and M is the likelihood. This comes from our generative model. It tells us, if the world were in state S, how likely would we be to make observation O? This represents our forward model of how states generate observations. P of S given M is the prior over states. Before seeing any observations, what does our model tell us about which states are likely? This encodes our prior beliefs or expectations. P of O given M is the model evidence or marginal likelihood. This is the total probability of making observation O under model M, considering all possible hidden states. Mathematically, this is computed as the sum over all possible states S of P of O given S and M times P of S given M. This term serves as a normalization constant. The reason this formulation appears constantly in active inference, Bayesian filtering, and machine learning is that it perfectly captures the essence of inference under a generative model. We have a model M that generates states according to P of S given M, and those states generate observations according to P of O given S and M. When we observe O, we want to invert this generative process to infer the most likely states. This is called Bayesian inversion, and it's at the heart of how the brain might work according to predictive processing theories, how robots can localize themselves, how we do inference in hidden Markov models, and countless other applications. The key insight is that everything is conditional on M. We're not asking for the absolute probability of states given observations, but rather, given that we're assuming a particular generative model M, what states best explain our observations? Different models M would give us different posteriors. To summarize the derivation, we started with the basic form of Bayes' theorem, applied the chain rule of probability to factor joint distributions, carefully kept track of all conditioning variables, and simplified by cancelling the common P of M term that appeared in both numerator and denominator. The result is the elegant form used in active inference and throughout Bayesian inference with generative models. This framework is incredibly powerful because it makes explicit the role of the generative model M, and shows us exactly how to update our beliefs about hidden states S in light of new observations O. This is the foundation of rational inference under uncertainty.